Hi everyone, and welcome to today's Chemistry Daily Booster. Do note this is for paper 2, so this is our first daily booster for paper 2. We've just had to start it before the first chemistry paper because otherwise they just won't fit between the two. So the first 3 are going to be before paper 1, but there's no harm in that anyway. What we're going to be doing then is having a look at a couple of the key groups on the periodic table in our booster today. Now, what we know is, hopefully, that group 1 are also known as the alkali metals. So as far as group 1 go, remember you get a periodic table in the exam paper. So when you look at it, you've obviously got this kind of overall structure of what the periodic table looks like. Group 1 is all the way over here, and they are referred to as the alkali metals. Now, what we find, group 1 are actually very reactive with our oxygen and water. Because of that, we have to store them in a slightly different way to other metals. We've got to store all of the group 1s in oil, and the reason for that, it prevents them reacting with oxygen and water in the air. This has been a question before on the chemistry papers, asking you why we store the group 1 metals in oil. And the answer is to stop them reacting with oxygen and water in the air. Please try to use those phrases. Don't just write to stop them reacting with the air, but be specific. Stops them reacting with oxygen and water in the air. Now, because they are metals, then we know that they are going to have some properties that are typical of all metals. They're shiny when they're freshly cut, they're good conductor of electricity, and they are solid at room temperature. So they've got those 3 properties in common with most other metals as well. We also need to know some key trends. Now, trends just means patterns. So there are some patterns as we go down the group. First one, they're softer the further down the group you go, which means they're easier to cut. You probably saw the demonstration of this in class where when you try and cut lithium, it's a little bit tricky. But by the time you're down to potassium, it's just like slicing through a bit of cheese, really, sort of soft cheese. The density also increases and the melting point decreases. This is the actual observations that you would have hopefully made from a demonstration and not some really naff video. So hopefully your science teacher did manage to chuck some of these alkali metals into some water so you could see what happened and get that lovely feeling of hydrogen catching in your throat in the lesson. So there are 3 that you would have seen in class. Lithium, the dull one, it fizzes slowly on the surface. It's quite boring, really. Sodium, a bit more exciting. When you throw sodium into the water, what happens is it literally melts on contact and turns into this molten ball, and it then zips around on the surface really quickly and fizzes quite a significant amount. When we get to potassium, this is where things get really good, because as soon as you throw it on the water, it instantly catches fire and it burns with a lilac flame. Please don't say purple. Lilac is the only answer here. Lilac is important. So it burns with this lilac flame. It moves around really quickly on the surface, fizzes lots, and if you're lucky, it exploded too. That's the sign of a proper chemistry experiment. Explosions. So what we would be expected to do is kind of describe what we would have seen here. Okay, so lithium, slowly fizzing, sodium, moving quickly, fizzing a lot, turned into the molten ball, potassium, burning with a lilac flame, moving very quickly, fizzing lots, may explode. As to what's actually happening here then, on the top line, we've got our general word equation. So this is just telling us what's happening without using the name of a specific metal. So metal plus water makes metal hydroxide plus hydrogen. To apply that to any of the alkali metals, all we're actually doing is changing the word metal for the name of said metal. So if we had lithium, lithium plus water makes lithium hydroxide plus hydrogen. If it was potassium, potassium plus water makes potassium hydroxide plus hydrogen. Pretty straightforward. Learn the general word equation, and then all you've got to do, shove the right metal in place. They can also ask us to do the balanced symbol equation for this. Now, if you're not great at balancing, you can learn this. That's the nice thing. Because all of group 1 react with water in the same way to make the same kind of product, all we're really doing here is writing the different element symbol for the metal. Everything else is going to be the same. So what we have is our metal plus water makes the metal hydroxide and hydrogen. So you can literally learn it as, if you want, you could just change the sort of name of the metal to just an X, so you remember that's just a metal. So it'd be 2X plus 2H2O makes 2XOH plus H2. Then in the exam, get your periodic table, whatever the name of the metal they're giving you, swap X for the metal, because the balancing will always be the same. 2's in front of everything except hydrogen. How do people throw away the marks on this? Because of hydrogen. If you write it so that rather than having H2, you've just written plus H, like hydrogen just goes around as a loner, you are going to get it completely wrong. That's both marks for your balanced equation gone, because that is not the correct symbol and your balancing will be all off. Hydrogen must be H2, goes around diatomic. If you get that, so if you were literally to write Na plus H2O makes NaOH plus H2, that's 1 mark. Stick the 2's in front of everything except hydrogen, there's your 2nd mark. Now, we've just kind of looked at one example of a reaction of the alkali metals by saying that when we throw them in water, basically they fizz and they get more reactive the further down they go. This is all linked into their electronic structure. Hopefully we do remember that because they're in group 1, they all have 1 electron in the outer shell. So if they ask you why anything reacts in the same way when it's in group 1, because they all have 1 electron in the outer shell is the answer. Please make sure you use the phrase outer shell and obviously state 1 electron. What we know in terms of our trend or our pattern is that reactivity increases as you go down the group. The reason for that is as we go down the group, and I've given you 2 examples here, sodium quite near the top on the left and then cesium near the bottom on the right. As we go down the group, we end up with more of those electron shells. So that outer shell electron is further from the nucleus. So if we have a look at sodium, we've got 1, 2, 3 shells, so that just has 3 shells. Whereas cesium, we've got 1, 2, 3, 4, 5, 6 shells there. So what we're actually able to see is this outer shell electron in cesium is much further from the nucleus than this outer shell electron in sodium. Because of that, it's easier to lose the outer shell electron from cesium. So that tells us it's going to be more reactive, because the further from the nucleus the outer shell electron is, the easier it is to lose, because there's a weaker force of attraction between the nucleus and that outer shell electron. So it's more reactive. So if they ask you to explain why group 1 get more reactive the further down we go, we need to talk about the fact that it's easier to lose the outer shell electron because that outer shell is further from the nucleus, so there is a weaker force of attraction between the nucleus and the outer shell electron. We are going to look at a second group, which is the noble gases, group 0 on our periodic table. So when we're looking at our lovely little set of the periodic table, it's these guys all the way on the right hand side. So the noble gases, group 0, they are obviously on the periodic table, you don't need to memorize them, and they're called the noble gases because they're unreactive. They don't really take part in many chemical reactions at all. Key things about our noble gases, they're non-metals. The right hand side of the periodic table tells us that. Their name tells us that they're all gases at room temperature. It's not some weird science trick, they are all gases. And they have full outer shells, hence why they are unreactive, because if something has a full outer shell, it just doesn't really react. We can use this word here, monatomic, which just means it's a single atom. Now, because they've got that full outer shell of electrons, they don't go around as a pair or anything. They literally go around as that lone little entity, the monatomic molecule. Now, each of those single atoms has very weak forces of attraction between them. Therefore, low boiling points, and they are gases at room temperature. In terms of the trends or the patterns in group 0, the further down the group we go, the attractive forces get stronger because those atoms are getting larger. Larger the atom, stronger the force of attraction between them. Because their forces are getting stronger, the boiling point is going to increase and they're going to have a higher density. You'll notice there are two little graphs at the bottom here. Now these are here because they can actually ask you to predict missing bits from these different groups. Now all of them has got group 0 here as the examples, but they could use any group. They could give you a table, they could give you a graph for this. What we need to do here is, yes, we know that this is going to go somewhere between this one and this one, but it's not quite as generous as long as it's anywhere between there you get the mark. There is a range, don't get me wrong, but be a little bit more careful. So actually work out the differences between these two. Work out the differences between those two, and then try to get a similar difference, obviously, to put your bar in here, okay? Same thing over here, you can see we've got increasing. Again, just work out the difference between the ones on either side and then try to apply that same pattern to get your missing bar or value in a table. It will be worth a single mark in terms of that, but in theory it's a relatively easy mark. You don't necessarily need to know anything about science to do. We're spotting patterns in data and then making a prediction based on that. Don't forget to join us tomorrow for our next Chemistry Daily Booster. Still be paper 2, and obviously if there are some bits that you want to go over in a bit more detail that we've done today, you've got the videos on the main channel that you can use. You can obviously use your revision guides that hopefully you all have, your classwork notes, and as always I do recommend having a look at some of the past exam papers as well on the OCR website. It just gives you a better feel for the kind of questions that can come up and what the acceptable answers are.